Okay, then the other one here was the ODE solvers. All right, so if you get nothing else out of numerical methods, I'd say there's a few things of value here, but being able to use these, I think, is really important. If you're doing anything that involves functions of time, and actually not even time, right? You can do this for any ODE that you have. So so in MATLAB, what you have is kind of the equivalent of the integral function in EES are these ODE solvers. So the ODE solvers are ways that are methods like canned methods that are built into MATLAB that automatically manage stepping in time or across whatever variable you have. So all you have to do is come up with, again, a way of evaluating dT/dt. So you're evaluating the state equation, but it can just be any function that you have. So let's say you don't even have an explicit relationship for your problem. You just have a function. It could be a lookup table. It could be some really complicated simulation that you're running. As long as you can return dT/dt given a time and the current temperature and any other arguments you have, these ODE solvers will automatically step through time and keep the problem and the solution stable for you. Okay, so it takes a lot of the thought, I guess, out of the solution process and lets you really focus on coming up with a really good state equation. So there's these different ODE solvers in MATLAB. One of the most general ones is called ODE45. I'd recommend you just go look at the documentation on this if you have questions on it, or ask me, I guess, too. But there is good documentation on this. The gist of it is that what you're trying to do is call this function ODE45. You're going to be evaluating it given the name of some function that you write. So you're writing some function, we'll call it dT/dt. And then you have to pass to it the span of time you want to evaluate over, and then the initial condition. Okay, so you pass these things, it will return to you a vector of time and a vector of temperature that have the same dimension. So temperature according to any specific time. So let's look at this real quick. Let's see here. Okay, so the example for this one is called ODE1. So here we see, so this is the entire function, right? So you have clear, and then we set the initial temperature. We set the time that we want to simulate over. This is up to 0.4 seconds. And then we have to write this function. We'll call it dT/dt Lecture13. So if I look here, this is my function to evaluate the state equation. So I have my constants, and then a few calculations, and then here's the evaluation of the state equation right here. Okay, so my function has to return this guy back to the ODE solver, but I'm taking in a specific time and a specific temperature and using that to evaluate. Okay, so we look back here. So this is the entire call, right? It's doing everything it's doing is right in this pretty much this one line here. Okay, so if I run this, let's see what it does. Okay, so I didn't plot the analytical solution, but basically you can see it's decided that this is the step size it wants to use. It steps through time, comes up with a solution. It's meeting the default error specification for the program. I'll show you how to set that. But this is what it says is a really highly accurate or sufficiently accurate solution. Yeah. I think for MATLAB, every function that you write has to be its own file. And the name of the file has to be the same as the name of the function. Yeah. Oh, can you? Okay, there you go. You can put the function at the bottom of the file if you want. Okay, so that's the ODE solver. Now, if you wanted to, let's say, so here in our example, we have written or hard-coded in our state equation function all these constants, but it might be nice to actually pass those constants as part of the function. So to do that, you have to do something called mapping. So mapping so let's look here first of all. So this is what we just had. This one here. Oh no, sorry, this is not it. Which one was it? Oh, well, so what we had, it was basically just a function of time and of temperature, right? So let's actually look at this. So if we wanted to pass extra arguments, we would then come in here and provide the name of the function, the name of the arguments we're passing, and any extra arguments. So we just kind of copy that whole function declaration that we have from right up here, right? This thing here. Just copy that over here. So we provide that as the name of the thing we're calling. Sorry, this is I'm getting ahead of myself. So this is what we kind of want to be able to do, right? We want to be able to pass something like this, but you actually can't pass anything that has these extra arguments. Okay, so don't want to confuse you. This is an example of what not to do, but what we'd like and ideally to do. Okay, so that's why it's commented out. So what we actually want to do is something called mapping, which does the following. So we say my function here, which I'm calling this, is going to return temperature and time for the ODE solver, but it's actually returning kind of more stuff than that, right? Or it could return more stuff than that. So we're mapping this function, which has a bunch of other arguments here, to something that's returning just, or is only a function of temperature and time. I sort of said that backwards again. So here, we'll say it again. So this function has all these arguments we're passing to it. So time, temperature, all this stuff. We have to map this to a function that only takes time and temperature. Okay. So this is how you do it. Just follow this. At time, temperature, and then the stuff you want to pass. Okay, and then if we look at our actual function declaration, we should see the function looks like this, right over here. So we can pass H, D, rho, K, C, and not the other stuff, or not worry about the other stuff. Okay, so let's do the same thing. Can solve it. It would have exactly the same solution. The other thing you might want to do is set options. So if you want to set options, there's this thing called ODE set. So you can look at the documentation for this. But among the options are setting the tolerances. So we could set the relative tolerance instead of 1e to the 4th or whatever it is, we could set it to 1e to the -8th if we want a really accurate solution. But if we do that, do the mapping, and then run this, hopefully it runs. You'll see that slight changes. So our time step actually becomes finer over here. But it's decided that it doesn't need to take a finer time step up here where things really aren't changing so much.